Welcome back, and now we'll continue the discussion that we kind of stopped in the last class, where we're looking at this. I think this is where we stopped, where we are talking about finding the CL and alpha using method one, where we start with some, initial guess of Fi, and then finding the values, and then change the. So the other ways to iteratively solve, so that is what we call it a method two, where you solve. So this is where you solve A and A prime iteratively. Okay, this is a method to solve this. So here we are trying to do iterating to find. So since as the mm, name suggests that we are trying to solve iteratively. So here we iterating to find out the axial and tangential momentum factor. So here is the axial induction factor. A prime is the tangential induction factor. So iteratively we try to solve that. But obviously when you iteratively solve, you need some initial guess. Okay. And so to find initial values, we start with the values from a adjacent blade section and values from the various or previous blade design in the iterative rotor design procedure, or use an estimate based on the design value. Something that we have to use. So importantly, what it is required is that we kind of start with an initial guess, and these guesses can be values from the, as I said, the adjacent blade section. This could be from previous design in the iterative rotor design process. That could be method one, or use an estimate based on the design values from optimum blade design. So what we get, let's say what we start with Phi1 is 2/3 tan inverse 1 by lambda Ri, which is, then we get AI1 1 by 1 plus 4 sine square Phi1 sigma prime I design CL design cos phi I1. So this is what you get, and then A prime I1 1 minus 3 I1 4 A I1 minus 1. Okay. So this is what would allow you to get the P flow angle, axial induction factor AI, and A prime AI. So now we use some guess value for that and move to the jth iteration for using guess values. We move on jth iteration, where j equals to 1 is first iteration. So these are all we kind of getting. These are all values are for first iteration. So what we calculate the angle of relative wind. So that means tan phi ij, which is 1 minus aij by omega r 1 plus k prime ij or it is 1 minus aij 1 plus a prime ij lambda ri. So that means if j equals to 1, that is the initial values of ai1, a prime i1 that can be used, and we can move on j2 like that. Similarly, the t plus factor, if ij, it would be 2 by pi cos inverse exponential b by 2 1 minus ri by r, and ri by r sine pi ij. So that's what we get in as an Fij. Now what we need to estimate is the CLij and CDij from airfoil lift and drag data. So what we can determine CLij and CDij from airfoil lift and drag data. So where we can use alpha ij equals to Pij minus theta Pij, which is essentially the angle of attack with the flow angle and the pitch angle. So now we can calculate local thrust coefficient. Local thrust coefficient, which is Ctij or Ctrij sigma I prime 1 minus a ij square CLij cos Pij CDij sin Pij divided by sin square ij. So we can update a and a prime for the next iteration. If local thrust coefficient Ctrij less than 0.96, then we can use ai j plus 1 equals to 1 by 1 plus 4 f sine square phi ij. We have sigma prime I CLij cos phi ij. So that is what we, so it depends on the local thrust coefficient. So if it is less than 0.96, that means it is in that area of the curve, because CT versus A varies like this. So this is 1, this is 1. So it is this side where windmill operation, and this is the turbulent side. So, and if Ctrij greater than 0.96, we have Aij 1 by f ij 0.143 0203 0.889 minus ij. Okay, and here we'll update a prime ij plus 1 equals to 1 by 4 if ij cos pij minus 1 divided by sigma prime CLij. So that gives us obviously sigma prime, it has to be I. So this is what you get, depends on the local thrust coefficient that you get to estimate these things. Now what one has to check, whatever the new induction factor that it has been obtained, these are acceptable tolerance limit or within the acceptable tolerance limit, then the others parameter can be calculated, and if not, then the procedure starts again with equation. So if converged, then stop or start the procedure equation 78. That means again we go back there and start with this iteration process. Now once we have solved the equation for performance, so once performance at each blade section or element is solved, then the power coefficient, we can find out the power coefficient, which is Cp summation of I equals to 1 to n lambda r by lambda square Fi sine square Phi cos Phi lambda ri sine Phi I cos Phi into 1 minus Cd by Cl cot Phi into lambda square Ri. So if the total length of the hub and blade is assumed to be divided into n equal blade elements, so basically the total length of the hub and blade by n equal length, what we have till r is I minus lambda r I, which is lambda by n. So what we can get that Cp is 8 by lambda n summation of I equals to k to n Fi sine square Phi Phi Ri Phi sine Phi cos Phi 1 minus Cd by Cl what phi lambda ri square. Okay. Uh, so where k is the index of the first blade section consisting actual blade airfoil. So you need to use the essentially you need to have the actual blade section which will have this data. So now if the design procedure is kind of complete, if all the parameters are within the acceptable tolerance limit, if the iterations have converged, then we can so we can put like this: if converged, we can stop here, or we can, or we need to repeat. We need to repeat the this design calculations once again, so that you get this design data of this. But this is how, I mean, you can have an idea how this rotor blade design procedure works, and how to estimate this parameter. So primarily you have to select the airfoil, you need to select some kind of a twist, you need to see the variation of the chord. I mean, obviously once you select the airfoil at different section, then the chord variations from hub to tip, and then considering those losses and factors, so that the induction factors is important, tangential induction factor is important. And obviously while doing that, you need those I mean the airfoil curve, like CL versus alpha curve, CD versus alpha curve, and the rest can process the, I mean, rest of the procedure can follow accordingly. So now what we can move on and look at, I mean, essentially now one can see this CP versus lambda curve. So once the blade has designed, I mean, once the blade has been designed, so this curve we can plot 0, 1. So this is lambda. This is so between here, it goes like this, and somewhere it falls down. Yeah, Jason. So once the blade has been designed for optimum operation at specified design speed ratio, the performance of the rotor over all expected tip speed ratios can be determined. So essentially, the optimum blade now used for various lambda. Um, for each tip speed ratio, the aerodynamic condition at each blade section can be determined, and this from there you can plot this kind of curve, and these curves are used in wind turbine design to determine. So this CP versus lambda curves are used in wind turbine design to determine rotor power for any combination of wind and rotor speed. So these curves are essentially important. So what they can do, they provide immediate information on the maximum rotor power coefficient and optimum tip speed ratio. So these curves provide maximum CP and lambda optimum. Okay. But obviously one has to be careful while finding these things. But variations in airfoil, lift or drag coefficients depend on the airfoil and the Reynolds number. So all this needs to be considered in this particular procedure. Okay. What we can look at it, we can look at some horizontal axis wind turbine performance uh, calculation procedure, which is a simplified version of that. So this was proposed by essentially proposed by Maxwell in 1990. So he proposed a simplified calculation for performing this horizontal axis wind turbine rotor, which is particularly applicable for an unstalled rotor. If the rotor is getting stalled, then this analysis cannot be applied. But also it could be useful for certain stall conditions. Um, Obviously, this method also uses the blade element theory that we have talked about and also incorporate those analytical method for finding the angle of attack, CL, induction factors. Now, depending on the tip loss, whether included, few or no iterations are required. If you include tip loss, definitely it goes in some iterative procedure. If you do not include the tip loss, then this doesn't include anything. So obviously there are two conditions which it applies. Number one, the airfoil section, the airfoil section lift coefficient versus alpha relation must be linear in the region of interest, which is simply tells that you stay within that linear variation of the CL versus alpha curve, which is before stall. Okay. Two, the alpha is small enough that small angle approximation may be used, which is sine of alpha would be equivalent to alpha. So that is very, very important. That means one is that you stay within the linear variation. Okay. You stay within that linear variation of the CL versus alpha. And then you kind of also say that the alpha is small enough. And then you can use this small angle. So one can immediately, those who are familiar with the airfoil theory or airfoil aerodynamics, this clearly indicates this is applicable for unstalled region. I mean, this essentially you talked about CL versus alpha curve, and this is my stall, then you are trying to restrict yourself in this particular zone. Okay, so that means you try to stay within the unstall. But as I've said that it can be applied to some stalled conditions for moderate angle of attack if the lift curve can be linearized. Okay. Here this simplified method, this simplified method is same as method one. Okay, which we have already talked about, right? But obviously there are some exception. I mean, with exception of a simplification for determining alpha and CL for each blade section. The essence of this simplified method is the use of an analytical or closed form expression for finding the angle of attack of the relative wind at each blade element. So what it starts, so obviously this is with a small variation in the angle of attack. What you can write, the lift and drag curve. So the lift and drag curve can be approximated as CL equal to CL naught plus CL alpha into alpha, and CD equals to CD naught plus CD alpha 1 alpha CD alpha 2 alpha square. When the lift curve is linear and small angle approximations is used, so what we can show that alpha is minus Q2 plus minus Q2 square minus 4 Q1 Q2 divided by 2 Q3. Okay, so where you have Q1 equals to CL0 not D2 4F by sigma prime D1 sine theta P. You have Q2 equals to CL alpha D2 plus D1 CL naught minus 4F by sigma prime D1 cos theta P D2 sine theta P. Okay. And you have Q3, which is CL alpha D1 4F by sigma prime D2 cos theta P. D1 equals to cos theta P minus lambda r sine theta P, and D2 equals to sine theta P plus lambda r cos theta P. So what you can do, so basically if I plot this 0 to 10 So then this is -1, 1. So what can I can have one curve going like that and coming like that. So this is one. Then I have zero line. Then I have this line. Then I have this line. So this is exact variation. So this side is your variation of CL, axial induction factor. This is empirical CL. This is A, how this varies. So what happens is that using this approach, the angle of attack can be calculated using the given equations. Once the initial estimate that you have, then you can calculate the tip loss factor also. And then again, you can use the this equations to calculate the CL, drag coefficients, and lift coefficients, all this. So these simplified methods provides of angle of attack very close of those to more detailed method for operating the condition. So this was actually, though we call it a simplified method, but this can very closely predict the behavior of actual conditions. Obviously, depends on the airfoil and the flow conditions. As we have talked about, the applicability of this simplified method is essentially in this particular range where you are away from the stall region. But for certain high angle of attack stall conditions, this can be used also. So this is what how the design procedure work, and but we will see other parameters effect in other systems. Thank you.